Welcome to the first math club of the semester. Okay. So I am going to talk to you all today. This is field day, and we're talking about fields. How many of you know what a field is or have encountered it? Okay, so I'll put this fast and loose. A field is basically a mathematical structure where you can add and multiply, and if a is not zero, then you can solve the equation unique. Basically, that means you can divide by every non-zero element, right? Ax equals negative b, and now you can divide by a. That's what a field is. You can add, multiply, subtract, and divide as long as you're not dividing by zero. So I'm going to start off with some basics. Right. Nice question. This doesn't just apply to fields. This is for any number. How many of you have heard of a characteristic of a field or characteristic of array? Yeah, I'm just going to field. If F is a field, then one of two things happens. To one. The field always has an element that's called one. It's called a multiplicative identity. You multiply anything times one and you get itself back. So if you add one to itself a bunch of times, this is never zero. For any order. So keep adding one to itself, you never get back to zero. This probably jives more with your intuition, right? The easiest field that I can think of where you can add, multiply, and divide something by zero is the rational numbers. Or maybe even if you're a calculus fan, the real numbers. Now, if you take the real number one and you add itself to itself, you get two. Add it again, it's three, and it gets four. Is that ever zero? Of course not. What are we even talking about here, right? But it can happen. This is a possibility. The number zero over there is the number of prime number here. P is called the characteristic of the field. And it's the number of times you have to add one to itself to get back to zero. And its characteristic zero that never happens. So, for example, here are some fields, characteristic zero, more familiar perhaps. Q. Are you familiar with this notation? How many of you see this? This is the rational number. That's big. Set of fractions of integers such that the denominator is not zero. This is the rational numbers. Anyone know what's special about this particular field, characteristic zero? Characteristic zero contains Q. Any field of characteristic zero contains a copy of this field. All right. Anybody, can you see why that's true? Notice I said that one of my rules is field has this one. Okay, if it's characteristic 0. That means that this thing, no matter how big it is, once you set 0. That means that any field of characteristic 0 has to contain all the natural numbers. Right? Well, now you got the natural numbers in there. But you have to be able to subtract as well, right? So now you've got to throw the negatives and 0 in there. So any field of characteristic 0 has to contain a copy of the ordinary integers. Is that okay with that? And what's the smallest field that contains the integers? Well, basically, you have to go through and make sure that every integer that's not 0 has a reciprocal. Right? So the smallest economically field that could contain the integers has to also contain 1/2 and 1/3 and 1/5 and so forth and so on. And this is it. There are, of course, bigger fields, characteristic 0. Here's one right here. This field is to the rationals as the real numbers are to the complex numbers. This is the set of this is just like complex numbers, except I now demand that A and B not be real, they have to actually be rational. You can check that this is a field. In fact, if you have any non-zero element, what's the reciprocal of this? I feel like I'm back in grade school. I remember how they used to make you, oh, rationalize this, right? Well, here we go. And this is equal to A over A squared plus B squared plus negative B over A squared plus B squared. Rational number, and that denominator is not 0 because A and B can't. Right? That's a field. Here's one that you've seen in calculus. This is the real numbers, right? The reciprocal of the non-zero real number alpha is 1 over alpha. You add, subtract, multiply. This is all good. I don't want to make this talk too hard, but there is the complex numbers. What else? Can anybody else think of a field that you can build that's even bigger than the complex numbers? James? Right. The problem is that was not a field because you had the order of multiplication has to be computed. If you have any field, then this is rational functions with coefficients in that field. And you can add on another variable, another, and so forth. So you can see you can build fields like this. Any of you out there who are number theory fans, you probably don't have time, although this might be a subject for a good talk later, the p-adic rational numbers, that's another uncountable field. Yeah, all of these examples here are actually very big in the sense that they're uncountable. And of course, you could take the p-adic rationals and do rational functions over it. But what most people, or what you may not be familiar with at this point is, okay, here's a bunch of characteristic 0 fields. Is there a field of characteristic Notice I said before, I did it without proof, but I said like a field either has to have characteristic 0 or it has to have characteristic prime. If you're curious about that, ask me about it later, but it turns out that if your characteristic is not prime, it's possible for it to be a field. But is there one? Right, I said it had to have it, I didn't say it existed. And the answer is And I'm sorry for using this notation because I'm going to confuse it. Yeah, it's when I use this Z. How many of you have ever encountered this mathematical structure? Addition to multiplication model E. Maybe some of you haven't. So let me pick a page just for giggles and show you how it works. Jared, what's your favorite prime? Don't say 8675309.
37.
Yeah, minus 30. Okay, I'm gonna tell you how, because I said a few of those questions where you can add and multiply 5. So I'm gonna tell you how to add. You add two elements of this just like they're ordinary numbers without stupid little hats on them, right? And it's all well and good as long as you're less than 7, right? 1 bar plus 3 bar, 4 bar. 2 bar plus 4 bar, 6 bar, right? What happens if you go beyond what's in here? 5 bar plus 4 bar. Well, you treat it sort of like a clock. You cycle around, right? I mean, what time is it if you're 3 hours past 11 o'clock at night? Unless you're in wearing army fatigues, it is 2 o'clock, right? Because we don't have a 14 o'clock in here today, right? So what happens here? Oops, too big. So you get that, right? 5 plus 1, 2, 3, 4, right? It just cycles around like this. More formally, you can take this number, whatever you get, divide by 7, and take the remainder. Everybody okay with that? How do you multiply? The same way. Only it's probably easier to divide and take the remainder now. What should this be? 6 bar. And this is the way it works for every well, actually, it works for every n, which prime or not. This is the way the addition multiplication works. Everybody see how that works? By the way, or what in this field, I'm playing this field, what is 6 times 6? But I do it faster, you use 1. 6 is the same thing as -1, isn't it? If I agree with it, so that's the quickest way to do that, is square minus 1, right? But you can do it the long way, 36 divided by 7, take the remainder of 1, right? Okay. Does everybody believe we can add, subtract, multiply? How about divide? I'm going to prove that we can divide, but I'm going to show that everything has a multiplicative inverse. So in other words, if you have any element, it's reciprocals in there. What's the reciprocal of 1 bar? Or 1 bar. So I'm going to draw an arrow to itself like that. How about 2 bar? What can you multiply by 2 bar? That gives you 1 bar. It's 4, isn't it? 2 times 4 is 8, which is 1 here. How about 3 bar? What was that now?
5 bar.
Looks like it's 5 bar to me too. 3 times 5 is 15, which is 1. So. And what about 6 bar? Well, just like -1, it's its own reciprocal. So this is in fact a field. This is always a field. What is the key takeaway here? The key takeaway is all of these things had reciprocals. And why is that? Anybody know? Oh, that's right. So here is, so if you're in my 4120 class, you're gonna love this, you're gonna love it. P not by x. So suppose x is an integer. That doesn't apply to p. This means the GCD of x and p, the greatest common divisor of x and p is 1. Right, okay. So 41.2, what does that mean about x and p? Yes, I have beat you to death with this, right? There is a linear combination of x and p that is 1. Right, so there exists a, b, and z, such that ax plus p bp is equal to 1. Now reduce this mod p. This is divisible by p, isn't it? So mod p, this is 0. It's a multiple of p, so it's 0. So what we've shown is if you have anything that isn't divisible by p, so anything, any of these things, then it's got an inverse, right? Because what this translates to is a bar x bar equals 1 bar. Okay, any questions on that? So is that it? Right? I mean, so we've got finite fields, Z mod P, they're all finite. So I've got a field of order P, it's got P elements in it for every P. Are there more? Well, the answer is yes, and I can tell you something about what they look like. So facts about this. Number one, this is technical, and I put this in. Some of you may not know what this means. That's okay, because some will, and I'm not going to use the sentence later. But any finite subgroup of the non-zero elements of that are all invertible. Give a finite subgroup of this. Sick. So everything in there, there's a power that's big, a big enough power of it goes one, and it's generated by a single element. Two. Pretty much everything that you've ever done in Math 3110 or will do when you get there, you can do it over any form, right? A lot of linear algebra books are very practical. And of course, there are differences in things when you worry about reals and complexes, but most of what you do in field theory, vector spaces, or in linear algebra, they don't really depend, they don't centrally hinge on anything other than it's over a field. And I'm going to turn this into an advantage here. So, how many of you heard the buzzword vector spaces? Still in therapy, are you? So, a vector space, for our purposes today, and I only care about finite dimensional vector spaces, but think of a vector space today. A vector space is to a field as Rn is to the real numbers. Like in calculus, right? You start off in calculus and you're looking at calculus on the real line. Then you go to Calc 2, or I'm sorry, you go to Calc 3 and you do all this groovy stuff in 3 dimensions and so forth, right? And so you have a function z equals f of xy, right? And your domain is the entire plane, right? 2 copies of r. You've seen r, the plane written as r squared, right? Or sometimes r cross r. Well, that's what a vector space is. It's analog to a field. It's just some number of copies of that. Now, if we keep this in mind, suppose f is a finite field. Then F is a vector space over ZP. Now, do y'all remember how? Do you remember how the rational numbers was this contained in any field that has characteristic 0? It doesn't say, hey, you got 1 in there, so now you got all the integers. Now you've got all the quotients of that. Well, it's even easier for finite fields, because if you have a finite field, it's got 1 in it, and you keep adding 1 to itself until it gets to 0, which will be after p iterations, and that gives you a copy of ZP. You don't even have to worry about inverting stuff here, because automatically the stuff you've had is already inverted. Right? So if I walk up to you on the street and give you a finite field, it will contain a copy of ZP. And it will be a vector space over ZP. Just like the plane is over R, 2 copies of R, or space is over R, 3 copies of R. So F can be construed as some number of copies of ZP, and in exactly an analogous fashion to what happens in reals. And I do mean finite, because if there were infinitely many copies here, it wouldn't be finite anymore, now would it? Right? So we're fixing to hit a theorem here. If I have n times, so I'm filling up an n tuple, and in each tuple I've got p choices put in. How many ways are there to make an n tuple? Well, how many choices do I have to put here? There's p of them, right? And p forever. So if I'm making p choices in every slot, I've got n slots. How many choices can I make? The order of this number of elements is p n. So here it is, first theorem. If F is a finite field, then F has p to the n element, where p is characteristic of F and n number. We already know that a finite field exists for p to the 1 because it's CP. All right, it's the elements. Are the big, but right away, if somebody comes up to you and says, hey, check this out, on my naughty little notebook, I have come up with a field of 10 elements. Impossible. Can't be done because it's not a power of any kind. Right? But okay, what this tells us is the following. It says, hey, if you have a finite field out there somewhere in some Stephen King novel, then it has to have p to the n elements. That's what I know. And I do know that there are fields of order p, namely CP. I don't even know there's a field of order p squared, right? That's a possibility. Can anybody think of one? Given my notation up there, it might be well, any ideas? Yes.
I was just gonna say, maybe it would be just good to say that that's not a field, right? But it's just isomorphic as a vector space.
Yeah, this is vector space, right? But this is counting the finite. This is actually finite. This is isomorphic to the finite field F as a vector space, but not as a field. Right.
And,
But
right.
all we're doing is count the elements, so it doesn't matter.
How about Z2 on?
What's that?
How about Z2 going on for you?
That's Z2, right?
The smallest field.
You mean Z mod 2?
Yeah,
Right. And I is the square root of -1, right? Which
Yeah.
is square root of 1, so it's still just Z2.
oh, right, because x squared plus
Yeah,
one
you
is reducible over Z2,
Right. So,
or the root of x squared plus x plus one.
yeah, people are tempted to write ZP cross ZP, or maybe ZP squared, right? Unfortunately, neither one of those work. They're not fields. They have, in fact, they're worse in the following sense. You can find two non-zero elements in both of those structures and multiply together and you get zero. So it's hopeless for them to have an end. So is there a field of that order? Well, we're going to get to that in a moment. Let me give you kind of a neat little, let me kind of give you an answer to this question and then we'll try to address it. So the answer, so this is my spoiler here, is there exists a unique field. Unique up to isomorphism, but you can think of it's unique here. Of order e to the n for every prime p and n in the next one. So if you give me a prime 8675309 and an n 10, there does exist a field of that order. So, and I'll show you how to build them too. It turns out, here is kind of a fun thing. You can actually win bar best with this one. This one is called Fermat's Little Theorem. How many of you have ever seen Fermat's Little Theorem before? So you're probably going to encounter somewhere. You see it in algebra, you see it in number theory, you see it in coding theory. It's very big there. And here's what it says. There are many ways to state this. If P is prime, and A does not have a factor of P in its prime factorization, then A to the P minus 1 over 1. This is kind of a brutal thing to check, but so for example, without even looking, if I give you a prime, say 11, and it's some number 37, right? 37 is not divisible by 11, but I will give you that 37 to the 10th power, when you subtract 1 from it, it has to be divisible by 11. Right? That is actually a bit of magic. And it follows actually from some root theory, and it follows from some of the stuff that we've done, with a little bit more added to it. But you can see this in action with Z mod 7, right? One to the 6, which is P minus 1, over 1 mod 7. Is 1 minus 1, 0. 2 to the 6, which is 64 over 1 mod 7. 3 to the 6, which I guess is 29, so is equivalent to 1 mod 7. Right? And from here on, I'm done from here, right? I mean, I don't, but I really am done, right? Because what's 4? It's -3, right? And the 6th power of that, I've already done it, right? And 5 is -2, right? So I don't really have to do any more work beyond this. They all work. my earlier observation, if F is a finite, then F minus 0 is generated by a single element. Okay, let me tell you what I mean by this. What that means is, if you have a finite field, jerk out 0, it's gone. You can find a single element in what's left over, such that when you take the powers of it, it dances through all the non-zero elements. This is called a generator. And I tell you, it's not going to work, is it? There you go. So if you take x to be 3,
It's 2 squared is 2.
x squared is 9, which is 2. X cubed is, taking advantage of this little identity here, is 6. X4 is minus 3, which is 4. X5 is 5, and X6 is 15. This magic little X is a power to sweep through and get every non-zero element field. Any finite field must have this property. All right, because if you like the technical stuff, the non-zero or the finite subgroup of the non-zero elements of the field must be cyclic, so there must be something. And I'll give you a problem that if you solve it will be fortune and glory. 3 swept through everything, right? Do I agree with that? And so its inverse, which is 5, should sweep through everything. 2 does not, right? Because what happens, because 2 and 6 are not really, right? 2 goes 2, 4, and then 1, so it doesn't sweep through. Everybody okay with that? It is a long-standing conjecture that for infinitely many primes, 2 will do this dance all the way through. It's called a primitive element, right? So it is conjectured that for infinitely, obviously not for 7, but for infinitely many primes, 2 generates all the things it's with the powers. This is true mod 3, it's true mod 5, and it's true in a lot of cases. But it's been open since the time of Gauss. Nobody knows the answer to whether 2 is a primitive group for infinitely many primes or not. Okay, any questions so far?
Yeah, what is that called?
What's that?
What is the conjecture called?
It might be, it might have the words primitive element in it, right? But I think it's been open since Gauss's time. And it's, some of these like simple to state problems can be very bad. Right. So, here's what this all means to us. Suppose F is a finite field. Now, I haven't shown you any beyond Z mod P yet. Well, let's indulge me and let's assume these exist. Bring up the element, P to the n elements. It must have a generator of order P to the n minus 1. And what I mean by that is there's P to the n elements in the field. P minus 1, my bad. When I pull the 0 out, that's how many elements I have left. So there must be some, we'll call this generator A, such that there must be some A that travels through and gets all the non-zero elements of the field, and it should end with one, just like we did there. Everybody okay with that? If it exists, this happen. So A is a solution to a polynomial right? Because look, A to B to the n minus one equals one. So there you go. Must be a solution to this. And you know what? I dig this because notice, is zero a solution to this polynomial? No, it's not. So you know what I'm gonna do? Because I'm a big fat cheater. I'm gonna multiply this by x. This polynomial has zero as a solution, and if it doesn't have zero, then it has these other ones as well, right? Now, let me ask you a question. If you have a polynomial, okay, let's just pretend we're in pre-calculus. Suppose you have a polynomial and you have a multiple root here. I'm gonna assume that you've got, I'm gonna assume that you've got at least two factors of x. But okay, maybe I am using calculus, so forgive me for this. How do you take the derivative of this? Product rule, chain rule, right? So I'll take the derivative of this first. My calculus is not too rusty. Does that look right to y'all? What happens when you plug in A to this derivative? What do you get? What do you get here? You get zero because you get zero from this term and K's at least two. So you've got another positive, this is not zero. There's at least one other factor of x minus a. Agreed? So when I plug in this, I get zero. Let's do all this instead of doing it over the reals over ZP, but my derivative rules are the same. Huh. What's the derivative of this polynomial? What's the derivative of this? Yeah, no tricks here, just like the old days. And what's the derivative of this? This is zero. Why? Because the field is characteristic P. When you add one to itself P times, it's zero. So if you add anything to itself P times, it's zero. So the derivative of this polynomial is -1. Everybody agree with that? What happens when you plug any number in? Can you plug any number into this and get zero? It is impossible. What does that mean about this polynomial? It means it can't have multiple roots. How many roots do you suspect polynomial of degree P to the n to have? It has to have P to the n roots somewhere, right? And none of them are repeated. if you collect the roots, you have your field of order P at the end. So, f of x is x to the p to the n minus x, has distinct roots. And I'm gonna do some computations to kind of show you how this works. This sucker has distinct roots and e to the n of them. Roots form a field of p to the n elements. For ease of computation, I'm going to do my computations over. I'm going to show you how this works. So, well, let me start with a stupid example. And I'm going to do everything over Z2 just because it's easier to do the computations. This should be the roots of x to the 2 to the 1 minus x. And how about this? 0, 1, which was what we see in our field 2 elements. Everybody agree with that? No shock there. We already knew that's Z2. Let's up the voltage. Field of 4 elements. The polynomial here would be x to the 4 minus x. The field of 4 elements has to contain the field of 2 elements. That's one of the things we see. So we better see that polynomial showing up again. Well, actually, I'll go tell some status. This is the way this polynomial factors. Let's check me, but remember, we're mod 2, right? X4, check, right? X cubed minus x cubed. How about the quadratic term? X squared minus x squared. Check. Negative x. That's the way that this polynomial factor. Now, look in Z2. You've got 0 and 1. They're roots to this, right? Are either of those things roots to this? No, they're not. Plugging in 0 gives you 1, plugging in 1 gives you 1. Okay? So here's what the field of 4 elements looks like. 0 bar, 1 bar, omega, and omega plus 1. Say that where omega is a root of this, right? And let me show you how things work, because omega squared plus omega plus 1 equals 0. I've just sort of abstracted, constructed this omega that's a root of this, right? You might say, hey, Jim, this is supposed to be a field, it's supposed to be closed under multiplication. Where is omega squared? You add, and I'll say, well, here it is. But remember, characteristic 2, that's omega squared. And notice these two are inverses to each other, because omega times omega plus 1 is omega squared plus omega, which is 1. Because again, this equation. Right, really? Oh, it gets more fun. Let's look at a couple more. Let's look at the field 8 elements. This again contains the field of two elements. But it does not contain the field of four elements, as a matter of fact. Its polynomial is x to the eighth minus x, which is and you can, this was pretty easy to see. It turns out there are two and only two irreducible polynomials over Z2, and those are them. If you multiply this all out, you will get x to the eighth minus x. Here, and let me, from here on out, I'm making no distinctions between plus and minus, because in Z2, there's no distinction. So, what do we get here? This corresponds, these two roots correspond to F2. And then you've got these six other things. There are roots to these pair of polynomials. These are the elements of F8 minus F, well, Z2. Z2 and F2, I use some minus. It turns out that if you have a field that has one of the roots of this, it has to have the other two roots of this and all the roots of this as well. I'm going to do two more. I'll talk a little bit about the last one. The polynomial for the field of 16 elements this one has right. So x plus 1. Where are you now? There you go. X is 1. X squared plus x plus 1. 1, 2, 3, 4. We've got degree 12 to go. It turns out that there are exactly four irreducible polynomials, or I'm sorry, three irreducible polynomials of degree 4 over this, and they all have to appear in this factorization. And they are, I'll take it to another line. All right, now there we go. X4 plus x plus 1, x4 plus x cubed plus 1, and x4 plus x cubed plus x squared plus x plus 1. It turns out that these are the only three irreducible polynomials of degree 4 over the field of two elements. Any root of this generates a field of order 16, which means that this polynomial must contain all of the irreducibles, because there's only one field of order 16, and you've got to have them all. This corresponds to the F4 that's intermediate, and this is the base field down here. Now, just because I wanted to torture myself last night, I decided to give you a really big one. And I've got an amusing story that goes with this one. The polynomial here was x to the 64 plus the x's. Okay, hold on to your hats. X plus 1. Notice this 6 here tells me something. All its divisors are clues. This has to contain the intermediate extension of degree 2. So F4, it's got to contain the degree 3. So it's got to contain x squared plus x plus 1. It's got to have the two ones of order degree 3. And lucky us, it has to contain all irreducibles over Z2 of degree 6. Can you tell how many there have to be? So where are we so far? We're up to degree 10, right? 54 to go. Degree 9, there's 9 of them. So, here they are. And feel my pain. X6 plus X cubed plus 1.
You only really had to find half plus one.
What's that?
You only really had to find half plus one.
Well, yeah. Half plus 1 is right. Times X6 plus X4 plus X3 plus X plus 1. And this gives rise to X6 plus X5 plus X3 plus X2 plus 1. Then X6, 4, 2, 1. Right, so that should give rise to X6 plus X5 plus X4 plus X2 plus 1. And how about that on the 2 more to go? Times, and I'll put these in pairs here. X6 plus X5 plus X squared plus X plus 1. And that gives rise to X6 plus X5 plus X4 plus X plus 1. And that looks right. Let me make a note of how I do it, because there's a lot of irreducible polynomials at degree 6 of this. Let me first show you how things lie. Z2 is the smallest field here, and it's contained in all of them. Z2 contains F8, or is contained in F8 and F4, and both of them are contained in the field of word 64 here. And you can see this showing up here. This right here is the base field. That's the extension F4. This and this is F8. And the whole shebang is F64. Now, any questions on that? I will say one final remark, and this is yet another warning thing. So I'm a lazy man, and I was like, this has got to be on the internet. So I asked the computer a couple of nights ago, tell me what the six irreducible polynomials over the field of 2 elements are. It gave me, first of all, it told me there were 6. So I wrote, no, there have to be 9. Oh, yes, you're right. You know how I got this. Oh, yes, you're right. Here they are. No, that's wrong. Gave me another list. No, that's wrong. I went through this 8 times. They were all wrong. Right? I mean, I didn't know what the list was, but I knew what they were giving me was wrong. Do you know how I can tell? If I have this polynomial, I have to have this. Do you know why? When you make the substitution 1 over x and then multiply by x6, it's this polynomial. If it's a field, if you've got the element in there, you have to have its reciprocal somewhere. So every one of these pairs off. And you might say, well, Jim, what about the fact that there's 9? This one pairs off with itself. So AI kept giving me the same list, well, the different lists. They would, oh yeah, you're right, this one was wrong. And then 2 steps later would put it back in the list. I mean, it was unbelievable. So Jared and I worked with some high school kids at this MIT Times program, and one of our students got on and got the list, and it was the only one that I had seen that didn't have a contradiction in it. I was like, oh, this must be it. I put it in the group chat. So I copied it in the group chat. And I got all, after our meeting was done, I pulled out what I had copied and I pulled it up, and the polynomials were all truncated at degree 1 because the picture wasn't right. So I lost everything. And I went through another 8 of it telling me the wrong thing. And so finally what I did was, so how did I figure out what they were? Because there's a lot of them to count. Here's how you figure it out. All right. If it's irreducible, you don't want it to have a root of 0, right? So it's got to end in one. That's easy for Z2. So it's got to end in one. And it's got an odd number of terms. It has to have an odd number of non-zero terms. Why is that? I don't want it to have a root one either, right? So that throws this out. So all these things, if you notice, they should have an odd number of terms in it. And if I find one, that little trick I showed you finds another as well. And so a 6-degree polynomial, if it doesn't have a root, right, and it reduces, if it breaks down, then it can't break down into a degree 1 and a degree 5, right? So it has to break down, if it's degree 6, into irreducible 4 and a 2, or some 3s, right? Well, there's only 2 irreducible polynomials of degree 3. We saw that before. So call them Fred and Ethel. Square of Fred, Ethel, Ethel squared. Those 3 have to be reducible, so I threw them out, right? And then all the rest of them, you can just see if they're divisible by the 1 quadratic irreducible. That's the way I finally get it. So biological trumps artificial yet again. Okay, any questions? Any questions? All right, well, go home and do all the stuff I did with like the field of 3 elements and see how long it takes you to weave the tapestry of profanity. Other questions? Yeah. All right, y'all have a good weekend. Stay tuned. We have a big stuff.